So far we have seen how to apply Newton's second law to a singular particle, right? So if you have a single particle P and you have a bunch of forces acting on it, let's say F1, F2, F3, and so on, maybe up to n, Fn, then you can add all these forces, F1 plus F2 up to Fn, and that would be equal to the mass of the particle times its acceleration, right? So in short, we will write all these forces as sigma Fi, where I changes from 1 to n, right? This is the shorthand notation we'll be using to indicate a summation of large number of forces or any other variable, and that is equal to mass times acceleration. And that has been fine. We can count the number of forces, we can add them vectorially and then equate them with mass times acceleration, and that was our balance laws. In combination with the kinematic analysis and balance laws and the force laws, we could solve the problems in this chapter. Now the next question is, how do we solve similar problems for a system of particles? So a system of particles is basically a system consisting of a large number of particles. There could be 2 particles, 3 particles, up to n particles, right? So let's say we are talking about a one particular particle Pi in here, right? And I is changing from 1 to n. So you have n particles in the system. So first of all, what kind of particles we are talking about over here? Well, particles are nothing but idealization of physical objects, right? And that's what we're doing in this chapter. So you could have multiple blocks connected by multiple pulleys, and we have seen examples of those in the previous module. Each of those blocks could become a particle, which are connected to one another via cables or the strings. And what are the cables and the strings doing to different blocks? They are applying tension or the forces on one another, right? You could have, let's say 3 books piling on top of each other, and each of them are particles, and all those particles are exerting forces on each other, right? How? Not via normal reactions, right? So you could have particles that are connected to each other, or you could have particles that are not connected to each other. So it could be a system of loosely connected particles or a system of rigidly connected particles. So it doesn't matter, what system you're talking about. Okay, and this system of particle notion is actually quite prevalent in molecular dynamics, where you have different molecules or atoms, and they're interacting with each other via some sort of forces, and you're trying to figure out, what their motion would be as a result of, the complex interaction of the forces among the particles. So let's say, we have a system of particles where we have all these n number of particles, and we want to understand how we can apply Newton's second law to the system. So let's just focus on one of the particles over here, okay? So Pi is the focus of our particle. Let's say that Pi is interacting with all the particles in its vicinity, and they are all applying some sort of internal force on the Pi, okay? So on particle Pi, we have internal forces. So internal forces. So internal are the internal forces internal to the system on Pi are basically what we'll call Pi1, Pi2, Pi3, and so on. So these are the forces that are being applied by, other particles other than Pi. So Pi1 is the force on Pi from P1, Pi2 is the force on Pi from P2, and Pi3 is the force on Pi from P3, and so on, right? And of course, I should not be equal to 1, 2, or 3 in this case, right? So you will leave one of the particles out too. Otherwise, you'll be counting internal forces on a particle by itself, which could happen, but let's say that's not the case over here. Okay, and then you can also have external forces on Pi, right? So what are the external forces on Pi? So the forces that are external to the system are the external forces. So let's say we have a force on Pi called, we'll call it, let's say Fi, okay? Let's say F is for external. So Fi is the force that is externally applied to this particle. Now, Fi may not necessarily be just one single force. Maybe there are 3 external forces that are acting on Pi, but we are just going to sum them together and cumulatively call all those 3 forces, external forces, as single force Fi, okay? So if you draw free body diagram of Pi, and I'm going to draw this separately now. So this is the Pi. You have Pi1, you have Pi2. These are all internal forces from n particles. In this case, it will be n minus 1, leaving itself out. And then you have force Fi, which is your external force. So on one single particle, we can always apply Newton's second law, right? So we can do that. We can say sigma F on Pi is equal to m times acceleration of particle I, right? So we'll write a sigma Fi to indicate the forces acting on particle Pi. So what are the forces? We have Fi, which is your external force, plus Pi1 plus Pi2, and all of these vector quantities up to Pin, and that is equal to m times acceleration of Ai, right? Okay, so we get one equation of this sort, right? Similarly, we can write this equation for another particle, let's say Pj, right? And we will have a similar equation like this. So if I have n particles, I will have essentially n such equations. I'll have n such equation, right? Okay, so if I have n such equation and I, let's say, add them all, what am I going to get? Well, let's look at it. So if we add all the forces that are on the left hand side, we will clearly have the sum of all the external forces, right? So we will have something like F1 plus F2 plus F3 up to Fn, and these are all the external forces. These are the forces that are external to the system, and then we will have internal forces. So we'll have Pi1 plus Pi2, so on, right? But all of these internal forces, because of Newton's third law, occur in pair, right? So Pi1 is the force on Pi from P1, and then P1I is the force on P1 from Pi, and both of these are equivalent magnitude but opposite in direction. So all the internal forces occur pairwise, and they're equal in magnitude but opposite in direction. So if you add them all, they will actually cancel out to zero, right? So on the left hand side, you will essentially have just the external forces, okay? And on the right hand side, you will have m times acceleration. Let me call this mi. M times acceleration for each particle added together. So on the right hand side, you will have sigma mi acceleration ai, where I changes from 1 to n, right? So if you can't see how the forces are cancelling out, let's do a simple example for two particle case. So I have a system with two particles, P1 and P2. Okay, internal force on P1 from P2 is P12, internal force on P2 from P1 is P21, and P12 is equal to minus P21, right, because of Newton's third law. And you have external force on this as F1, external force on this as F2. So for particle 1, I can write F1 plus P12 equal to m1 times acceleration of 1, and for particle 2, I can write this, okay, 1 and 2, and I can add them together. If I add them together, I get F1 plus F2 plus P12 plus P21 equal to m1 a1 plus m2 a2, right? But P12 is equal to minus P21 from here, right? That means this is 0. So what we are left with is this equal to m1 a1 plus m2 a2, right? And this is the result that we have generalized right over here, where we basically have just the sum of external forces equal to sigma mi ai, right? Okay, so general equation is sigma fi, I changing from 1 to n, these are all external forces, equal to mi ai. But ai can also be written as d2 over dt2 of position vector of I, right? So for this, we need a coordinate system. So let's say this is my coordinate system, and that's the position of particle I. Okay. If the mass is not changing, that means it's a closed system. If that means the particles are not coming in and the particles not leaving out, then the mass is constant, and I can write this as d2 dt2 times mi rit, right? And this is summation, so I could do this as that, right? Now what is this quantity sigma mi rit? Sigma mi rit is nothing but mass times the position vector of the center of mass, right? This is how we determine the center of mass. So if I have a bunch of particles and I pick a coordinate system and I indicate the positions, let's say r1, r2, r3, so on, and I know their masses m1, m2, m3, and I want to find out where the center of mass of this system of particles is, unless the center of mass is given by this position vector r sub g, then it is obtained by multiplying each of these masses with their position vector, adding them together, and that is equal to sum of all the masses, okay, times the position vector of center of mass. And sigma mi will call as the total mass times, and then we have position vector. So this quantity is equal to this, right, which is what we have over here. Okay, so that means that this can also be written as m times d2 dt2 of Rg. And what is this quantity? This is nothing but acceleration of center of mass. So what we obtain is sigma Fi equal to m times acceleration of center of mass. Now that's a very good result. What this is saying is that if you have a system of particles and you want to write Newton's second law for more than one particle, and you can choose how many particles you want, right? You can choose that, and you can draw the free body diagram. You can show all the external forces. You don't have to show the internal forces. This is what it's telling you. You don't have to worry about the internal forces. You just sum all the external forces, and on the right hand side you write m times the acceleration of their center of mass, and that will be the equation that you'll apply for a system of particles.